Hello everyone, welcome to Wings of Physics. Myself Dipali Kulkarni from PVP Junior College, Pravaranagar, Loni. We will continue our topic Thermodynamics, and today's lecture is lecture number 14. In this lecture, we will study about the most important and difficult topic of this chapter, that is Carnot Engine and Carnot Cycle. After that, we will study the Carnot Refrigerator. So, let us start. Carnot Engine, that is proposed by a French physicist as well as an engineer, Carnot Cycle, in 1824. The elements of its engine are the source. Source is having infinite heat capacity and it is at a very high temperature TH. What is the meaning of infinite heat capacity? Means that a source is at very high temperature. We extract some amount of heat, its temperature does not change. Means its temperature is constant. Though we extract heat from that source, its temperature remains constant, and that is called as a infinite heat capacity, and boundary of the source, that is perfectly conducting. Understood? This is the first element of its heat engine, Carnot's heat engine. Second element, that is sink. Sink is also having a infinite heat capacity. Means if we extract heat, its temperature does not change. Means sink is also at a constant temperature Tc, and its boundary is also a conducting. Understood? Then third component of the Carnot engine, that is a stand, and that is perfectly insulator. Okay, means its boundary is of that stand, that is perfectly insulating. Boundary of source and sink, that is perfectly conducting, and boundary of stand, that is perfectly insulating. And we consider a system that is nothing but a cylinder, and inside that cylinder a ideal gas is a working substance. Ideal gas is a working substance that is fitted with a frictionless piston. That ideal gas is fitted with frictionless piston. Then walls of this cylinder, that is perfectly insulating. Walls are perfectly insulating. But its base of this cylinder, that is perfectly conducting. Understood? And this is the system that Carnot consider for the Carnot engine. Understood? I repeat. Cylinder is there. Cylinder is filled with ideal gas. That ideal gas is a working substance for Carnot engine. Then the walls of this cylinder, that is perfectly insulating. Its base is perfectly conducting, and that cylinder is fitted with frictionless piston. Okay. Now we have to consider the cycle, Carnot cycle. We have to consider 4 different stages. In first stage, we kept this system on source, okay, which is at constant higher temperature TH, and its boundary is perfectly conducting. Base is conducting, boundary of source is conducting. Then there is a exchange of heat, but due to the constant temperature, exchange of heat means transfer of heat from source to system is there, but it is at constant temperature, and due to the heat absorption, the expansion is there. Suppose initial stage of this system is P1 is the pressure, V1 is the volume and TH is the temperature, and due to the absorption of heat, the volume of this gas goes on increasing, and the volume goes on increasing means it goes on increasing from V1 to V2. Volume goes on increasing, pressure goes on decreasing, P1 to P2, and temperature remains constant. Means what happened in first case? When we kept this cylinder on a source, at that time a isothermal expansion is there because temperature remains constant, and isothermal expansion, that is reversible process. Okay, reversible process, that is nothing but a quasi-static process, means that occurs very slow, so that thermodynamic equilibrium of the system that should remain constant or that should maintain. And to maintain the thermodynamic equilibrium of the system, the isothermal process, it is a very slow process. Volume goes on increasing, pressure goes on decreasing, and heat absorbed by the system. Consider this case. Means when we kept a cylinder on the source, at that time the volume goes on increasing, pressure goes on decreasing, and work done is there due to the expansion of a gas. And according to the first law of thermodynamics, Q that is equal to delta U plus W, and the QH is the heat absorbed by the system. Means during, this is the diagram, PV diagram for Carnot cycle, and AB, this change when we kept the system or the cylinder on source, then that change is denoted with the help of AB curve. A is the starting variables, state variable, and B is the final variables during that change. Okay, and this is the heat, QH is the heat absorbed during that case. Now we have to apply first law of thermodynamics for this process. Then when at constant temperature, internal energy that is always equal to 0, because we know that internal energy depends on temperature, means this becomes 0, means Q that is equal to W. If QH is the heat absorbed and the work done, if we consider this work done as a W1, then heat absorbed QH that is equal to W1 in this case. Then according to the isothermal process, the work done is given by formula, the work done QH that is equal to the W1, and that is nothing but nRTH log to the base E V2 by V1, because V2 is final volume and V1 is the initial volume. Okay, log to the base E. This is the equation number 1. Means during the first step, during that AB change, this is the equation, and that is nothing but heat absorbed that is equal to work done. Now second case, we have to kept this system or this cylinder on a stand. In second case, we have to kept this system on a stand. Second step. Now the boundary of this stand, that is perfectly insulating, and due to that perfectly insulating boundary, no exchange of heat, QH that Q that is equal to 0, and Q that is equal to 0, at that time the adiabatic process is there. Means second case, adiabatic process is there. Now heat, in first case heat is absorbed by the system, and then when adiabatic process is there, at that time what happen? Q that is equal to change in internal energy plus W, and if Q that is equal to 0, then delta U that is equal to minus W, or W that is equal to minus delta U, change in internal energy. Now in this case, the system use change in internal energy due to the high temperature. The change in internal energy is there, and change in internal energy, again due to change in internal energy, the expansion is there, but Q that is equal to 0 and therefore that expansion is called as adiabatic expansion. And formula for adiabatic expansion, that is denoted by W2. Second case, that change is denoted by ABC in this case. Now system turns from adiabatic expansion is there. Now where initial variables are P2, V2, TH. Now the volume goes on increasing from V2 to V3. Pressure goes on decreasing from P2 to P3, and temperature, due to adiabatic expansion, the temperature falls from TH to TC. Okay, now TH to TC, and we can write work done during that process, during adiabatic expansion is there. And due to adiabatic expansion, we know that NR TH for adiabatic expansion, initial minus final is there, and 1 minus gamma is there. This is the formula for adiabatic expansion process, and this is equation number 2, and this work done is considered as a W2. For adiabatic expansion, the temperature falls because during adiabatic expansion gas cools down, and temperature falls from TH to TC, and this is the work done during that change. Now our system variables are V3 is the volume, P3 is the pressure, and TC is the temperature. Now third step, now again kept this system on the sink, which is at constant temperature TC. Now boundary of the sink, that is perfectly conducting, and base is also perfectly conducting. Therefore there is an exchange of heat at constant temperature. But what happened? Due to temperature falling, when temperature decreases, what happened? Volume goes on decreasing. And change is at constant temperature TC. That is, volume goes on decreasing from V3 to V4. Volume goes on decreasing. Pressure, volume goes on decreasing. Direction of volume is reverse, V3 to V4. Pressure goes on increasing from P3 to P4, but temperature remains constant. Means this is the initial variable during the change CD, and this is the final variable, and that change, but due to temperature fall, okay, now temperature of gas is low, and therefore the change occurs at constant temperature, and if temperature falling, at that time the compression is there, and that compression is called as isothermal compression. Again, that is very slow process, quasi-static process, so that thermodynamic equilibrium of the system that should maintain. Okay, and therefore the formula, and now heat is rejected. In this case, heat is rejected. Then third case, QC is heat rejected. Like again, Q that is equal to delta U plus W, but change in internal energy is 0 for isothermal process. Then QC that is equal to W3, and therefore QC that is equal to W3. Then formula is NR TC is there, log of V4. This is equation number 1. V4 is the final volume, and V3 is the initial volume. This is equation number 3. Okay. Now again kept that system on a stand. Fourth case. Now initial variable of the system are this one, V4, P4, TC. Here the initial variable. Now system change. If we kept that system on a stand, again what happened? The boundary of the stand, that is perfectly insulating, though base is perfectly conducting, no exchange of heat is there, means Q that is equal to 0. But what happen? Then temperature, the compression is there because volume goes on decreasing and therefore adiabatic compression is there. Adiabatic compression is there. Then variables changes from V4, P4, Tc, that is the variable, initial variable. It goes on changing. Then adiabatic compression is there. In adiabatic compression, the temperature goes on increasing, means temperature goes on increasing from Tc to Th. Then volume goes on decreasing, V1. Pressure goes on increasing. See here, pressure goes on increasing, volume goes on decreasing, pressure goes on increasing from P4 to P1 and temperature goes on increasing from Tc to Th. Understood? And the equation for that adiabatic compression, equation number 4, that is W4, that is equal to Nr Tc minus Th. Okay, final minus initial. Then Tc minus Th divided by 1 minus gamma, equation number 4. Now we have to calculate total work done and system return to its initial state. Means Carnot engine, the process in that engine, they are reversible and cyclic process. All process are reversible and cyclic process, and in case of a cyclic process, system return to its initial state and internal energy is a state function and therefore change in internal energy that is equal to 0 in this case. Okay. Now during this adiabatic expansion and adiabatic compression, what is the total work done? The total work done, if we add W2 and W4, that becomes 0. Means during that total change, adiabatic expansion and adiabatic expansion, total work done is 0. Now we have to calculate the efficiency. Understood? I repeat, in first case, we kept this system on a source, then adiabatic expansion is there. In second case, we kept this system on stand, then adiabatic in first case, isothermal expansion is there. When we kept that system on stand, then adiabatic expansion is there. When we kept that system on sink, then isothermal compression is there. And again when we kept that system on stand, then the adiabatic compression is there. And so in Carnot engine, 2 isothermal process and 2 adiabatic process are there. Understood? In isothermal expansion, heat is absorbed, and in isothermal compression, heat is rejected. QH is the heat absorbed and QC is the heat rejected. Now we have to obtain the derivation for the efficiency of this Carnot engine, and this cycle is called as a Carnot cycle. Okay. Now we have to calculate the efficiency of this Carnot heat engine. Okay. Then we know that formula for efficiency. Efficiency is denoted by a formula work done divided by heat absorbed. Then total work done. Total work done, that is nothing but the work done during isothermal expansion and work done during isothermal compression. We have to add these two things. Then the W, that is nothing but summation of W1 plus W3, and that is NR TH log to the base E V2 by V1 plus NR TC log to the base V4 log to the base E V4 by V3 and divided by value of QH, that is nothing but W1, and that is NR TH log to the base E V2 by V1. Now we have to obtain the relation between V2 by V1 that and in between V4 by V3. For that purpose, consider this adiabatic expansion. And for adiabatic expansion, the relation between temperature and volume, that is Tv raised to gamma minus 1, that is equal to constant. This is the relation for adiabatic change. Adiabatic change. Then apply the relation for these 2 points B and C. At point B, TH is the temperature and V2 is the volume, V2 raised to gamma minus 1. Then at point C, TC is the temperature and V3 is the volume, gamma minus 1. Okay, consider this is equation A. Now, during this adiabatic compression, consider these 2 points D and A. Then at point A, temperature is TH, volume is V1, gamma minus 1. And at point D, V4 is the TC is the temperature and V4 is the volume, gamma minus 1. Now divide equation A by B. We can write this TH that gets cancelled, TC that gets cancelled, and V2 by V1 raised to gamma minus 1, that is equal to V3 by V4 raised to gamma minus 1. Okay. Now this gamma minus 1 that gets cancelled, and V2 by V1, that is equal to V3 by V4. Then we can write value of this V3 by V4, then that is nothing but the V4 by V3, that is equal to V3 by V4 raised to minus 1. Okay. And if we substitute this V4 by V3, that is equal to V3 by V4 raised to minus 4 here. V3 by V4 raised to minus 1. Then in the sign of log of sign, now this minus 1, this becomes here minus, and value of this V3 by V4, we can substitute V2 by V1 here. Okay. Minus sign transfer here and it becomes V2 by V1. Okay. Understood this? Now, this NR that gets cancelled, and if TH minus TC that is taken as common outside the bracket, log to the base E V2 by V1 divided by this TH log to the base E V2 minus V1 is here. These two quantities that gets cancelled, and efficiency of Carnot heat engine that becomes TH minus TC by TH, that is nothing but 1 minus TC by TH. Okay. This is the formula for efficiency, means the efficiency of Carnot heat engine, that is equal to this one. For maximum efficiency, I already told you, in case of a heat engine, TH should be large, TC should be small. Okay. And therefore, for maximum efficiency, TH is kept as large as possible and TC should be kept as small as possible. And Carnot engine, that engine is having a maximum efficiency. It does not exist in practice. It is a ideal, imaginary, hypothetical engine. Okay. And it is proposed by Nicholas Leonard Sadi Carnot in 1824. But a bad luck is that he is having life, very short life. In the age of 36, he passed away. That is a bad luck. Okay. And this is all about Carnot engine. Are you getting my point? the derivation for this is not given in your book, but for CET, NEET, JEE, I explain that formula. Okay, now we have to study about the Carnot refrigerator. Carnot refrigerator. We already studied in case of a refrigerator. Refrigerator, that is nothing but a reverse heat engine. Means Carnot engine when operate in a reverse direction, that is nothing but a Carnot refrigerator. In refrigerator, heat extract from colder region. With the help of compressor we have to do work, and then heat is rejected to the atmosphere. In most of the cases, sink is nothing but the atmosphere. In all heat engine, sink is the atmosphere. Understood? Then we have to study about Carnot refrigerator. Coefficient of performance of a Carnot refrigerator, COP, that is denoted by value K, and formula for K, that is equal to QC by W. Then work done for this case, that is QC divided by QH minus QC. QH minus QC. This is the work done. Now divide each term of this equation by QH. Then QC by QH, QH by QH minus QC by QH. Then QC by QH 1 minus QC by QH. According to the Carnot theorem, QC by QH, that is equal to TC by TH. And if we substitute that value, then TC by TH divided by the 1 minus TC by TH, then it becomes TC by TH divided by, if TH is the LCM, then TH minus TC, then this TH that gets cancelled, and TC divided by TH minus TC. This is the formula for the coefficient of performance for a Carnot refrigerator. Means to COP should be large, means coefficient of performance of a Carnot refrigerator should be large. At that time TH minus TC should be small. Means this temperature difference between these two, means source and sink, that should be small. At that time coefficient of performance of a refrigerator, that should be large, or TC, that should be large due to direct proportion. TH minus TC, that should be small, and TC should be large. This is the condition for greater coefficient of performance for the Carnot refrigerator. I hope all of you understood this Carnot cycle, Carnot engine and Carnot refrigerator. If you like my video, then like, share and subscribe my channel, and also press the bell icon to get notified about my new upcoming videos. Thank you very much.